Introductory Chemistry, Chapter 6, Chemical Composition. So because atoms are exceedingly small, we have to have a way to talk about them on a realistic level. The unit for a mass on the atomic level is AMU, which stands for atomic mass unit. Carbon-12 was assigned the mass of exactly 12 AMUs. Carbon-12 meaning that I have 6 protons and 6 neutrons. Therefore, the atomic mass unit for any other element excuse me, is going to be 1.66 times 10 to the negative 24th grams. Negative 24 means that I'm a very, very small number. If I move this 24 places to the right, or sorry, to the left, put all those zeros in front, this is an exceedingly small amount of mass, which is not relevant for something that we can measure in the lab. So instead of measuring in atomic mass units, we're going to measure with grams because we have a balance that we can measure things in grams. So on your periodic table, the number underneath your element is its atomic weight. We'll see that the atomic weight in AMU is the same thing as the atomic weight or the molecular weight in grams. So we use the mole as a practical unit for defining a large number of extremely small particles. It works the same way as any other counting unit. So this is our relationship that we have to focus on. That a mole can represent anything. It is simply a number. It is a counting number. The same way that a dozen is always 12, a gross is always 144, and a pair is always 2. That means that whether I have a dozen donuts, a dozen eggs, a dozen bunny rabbits, a dozen shoes, right? It always means 12. Regardless of what we're talking about, a dozen tells you you always have 12 of something. If I have a pair of shoes, a pair of socks, a pair of cats, a pair of hats, whatever, I always have 2. Pair means 2. Don't care about what we're talking about. The number is always 2. So Avogadro's number tells us how many things we have in the mole of something. So a mole is the same as a dozen, as a gross, as a pair, in that it is just counting. But a mole is extremely large. It tells us that if you have a mole of atoms, ions, molecules, bunny rabbits, cats, hats, glasses, shoes, whatever it is, it's 6.022 times 10 to the 23rd atoms. So what does that mean? I take this decimal point and I move it 23 places to the right, and I end up with a very, 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 very big number. Why? Because atoms are very, 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 very tiny. So let's make the connection. If I look at the periodic table and I look at the atomic weight of something, the unit for that is in AMUs. I can also look at that and say that the mass of a mole of that substance, of those atoms, is in grams. Or if I have 1 atom of fluorine, it's 19 AMUs. If I had 1 mole of fluorine atoms, it's 19 grams. So the take-home message here is whatever the mass is on the periodic table, that is the same number if we designate it the unit of AMU or if we designate it with a unit of grams per mole. In the last chapter, we talked about formula weight or molecular weight and how this relates then to a molar mass. So molar mass says I'm a mass, which is grams. I'm molar, which is moles, grams per mole. Formula weight says I'm going to look at my subscripts and determine how many I have of each of my atoms and then add those up. So H2 means I have 2 hydrogen atoms. The mass is 1.01. So 2 times 1.01 is 2.02. Now I've added on an oxygen. So I take my 2.02, I add 16, and I get 18.02. Now I've added on another oxygen. So 2 times 16 plus 2 times 0.101. Add those together, and I get 34.02. For sodium chloride, the mass of sodium is 22.99. The mass of chlorine is 35.45. Gives me a mass of 58.44. Now, with a compound like this where I have parentheses, it means that I have to distribute the number by multiplying by whatever the subscript is. So 2 times 1 versus 2 times 4. Excuse me. So this means I look up the mass, 3 times calcium, 2 times phosphorus, and 8 times oxygen. So the mass of calcium is 40.08, multiply by 3. Add that to 2 times 30.97 for phosphorus, and then add that to 8 times 16 for oxygen. The total then is 310.18. The units for all of these are grams per mole. So 2.02 grams per mole, 18.02 grams per mole, et cetera, et cetera. So then how can we convert between having a number of atoms, the moles of those atoms, and the mass of those atoms? Well, we have a little pyramid. If we look up here, if we start with a number of moles, my conversion factor is going to be the molar mass, which we just talked about how to determine. So to go from moles to mass, I multiply. To go from mass back to moles, I'm going to divide by a molar mass. If I start with moles and I want to know how many atoms I have, my number of atoms is always going to be a really, really large number, which means it's times 10 to the something. So to go from moles to number, I'm going to multiply by Avogadro's number. If I have a number of particles, I'm going to divide by Avogadro's number to get back to the number of moles. To go from a number of particles to a mass, I'm actually taking 2 steps in the pyramid. So first I have to multiply by Avogadro's number. If I'm going to go from number of particles to mass, I'm going to divide by Avogadro's number and then multiply by the molar mass. If I have a mass, I'm going to divide by the molar mass, which takes me to moles, and then I multiply by Avogadro's number to get to a number of particles. So basically, if you're on the sides of the pyramid here, it's a one-step process. If you're on the bottom of the pyramid, you're taking 2 steps, which means 2 parts of a picket fence. Practicing with conversions. So, how many moles are in 19 grams of lithium? We identify what the given information is and what we want to find. I'm given 19 grams. I want to find how many moles that is. Given, want. So I always put my given number on the top. In order to get to moles, I have to find the molar mass to divide by it. So 19 divided by 6.94, got that from the periodic table, gives me 2.7 moles of lithium. 2 sig figs, 2 sig figs. How many grams are in 3.8 moles of silver? I'm given 3.8. I want to find the mass in grams. So now I'm going to multiply by the molar mass. 3.8 times 107.87 gives me 410 grams, rounding to 2 sig figs. Keeping in mind that my moles here cancel with my moles here. Up here, my grams of lithium canceled with my grams of lithium. How many atoms are in 7.2 moles of W, which is tungsten? I have my moles. I want to know atoms. So anytime I'm looking at atoms, I'm going to involve Avogadro's number, 6.022 times 10 to the 23rd. In order to cancel out my moles, I have to multiply by Avogadro's number. I round to 2 sig figs to get 4.3 times 10 to the 23. Over here, I was given 3.5 times 10 to the 22. I want to find my moles, so I'm going to take my atoms, divide by Avogadro's number to get back to moles. And by doing that, I get 0.058 moles, and I have 2 sig figs since 2 sig figs were given in the problem. So with all of these conversions, right, we're always setting them up to be whatever you're given, and then you have to cancel out that information to get to what you want to find. And I just noticed here that this is a typo. This should be 4.3 times 10 to the 24th atoms. Don't judge your numbers, right? This is a small number. You can have a very small amount of moles. But keep in mind that when we're talking about a number of atoms, you're always going to have times 10 to the something, because in any part of a mole, whether you have a lot of moles or a decimal amount of moles, it's still representing a large number of those atoms, because atoms are so small that we have so many of them in one mole. How about when we want to look at a component, an atom that is making up an overall compound, to figure out how many atoms do we have overall, or how many moles do we have overall of a particular element in a compound? So now we look at how many moles of oxygen are in 2.781 moles of cobalt-2 nitrate. Here's my given information. Here's what I want to find. Moles of oxygen. I'm converting from moles to moles. So nowhere in that pyramid do I have going from moles to moles. I have to actually look at my individual compound. So what this compound tells me is that if I have 1 mole of it, I have 1 mole of cobalt atoms, I have 2 moles of nitrogen, and I have 6 moles of oxygen for 1 mole of a substance, right? It's just like if you have 1 pair of shoes, you actually have 2 shoes. Or if you have 1 dozen eggs, you have 12 eggs. So here, I'm going to take my given information and then multiply it by the number of moles of atoms I have per my individual compound. So since I have 6 moles of oxygen, I multiply that by 2.781 to give me 16.69 moles of oxygen. If I were to take this calculation one step further, and I wanted to know how many atoms of oxygen were present in this amount of moles, I would simply take this number and multiply by Avogadro's number to give me 1.005 times 10 to the 25th atoms. So what this says is, if I have 2.781 moles of cobalt-2 nitrate, I have 1.005 times 10 to the 25th atoms of oxygen. How many grams of manganese are in 691 grams of manganese 3 oxide? So once again, if I look at this, for every 1 mole of this compound, I have 2 moles of manganese, I have 3 moles of oxygen. So I'm using that information to go from grams to moles back to grams. So my first step that I have to take is to convert from moles. Moles is your interconnecting unit between mass and number of atoms. We get to moles because that's our counting, because 1 mole of anything equals 6.022 times 10 to the 23rd. Those moles can have a different mass based on the element, but the number that you have is always the same. So if you have 1 mole of manganese atoms, you have 1 mole of oxygen atoms, it means that you have the same number of atoms. They weigh differently, but the amount that you have is the same. So I look to calculate my molecular mass of manganese 3 oxide. So 2 times manganese plus 3 times the mass of oxygen gives me 157.88 grams per mole. I divide by the molar mass to get to moles. Then I look to see that for every 1 mole of my compound, I have 2 moles of manganese. So I'm multiplying by 2. This is what this ratio means. Then because I want to take it to mass, I look at what is the molar mass of just the manganese element. 54.94, found that on the periodic table, and I multiply. So in terms of math, I'm going to multiply all the numbers on top. I'm going to multiply all the numbers on the bottom. And then I'm going to take the numbers on the top and divide by the numbers on the bottom. This gives me 481 grams of manganese, which tells me then I have to have 210 grams of oxygen left over. Why? Conservation of mass. I have 691 to start. If I subtract 481, I have to have 210. Now, to practice this, you can set up the same thing and actually check to make sure that you do indeed have 210 grams of oxygen. What's going to change? This here and this here, because now we'd be looking at 3 moles of oxygen and the molar mass of oxygen. So practice that and see that you get 210. So we can also look at the mass percent composition of compounds. And when we study a mass percent, This means that we're looking at how much mass is each individual element contributing to the overall mass. So for example, if I have $1 worth of change and I have 2 quarters and I have 5 dimes, well, I've got a total of 7 coins. 2 out of 7 of those coins are my quarters, and 5 out of 7 of those coins are my dimes. So we can do a percentage, right? 2 divided by 7 times 100. 28.6% of my coins are quarters. If I subtract that from 100, I get 71.4% then has to be my dimes. So you're always adding up, or you have to total to 100% when you're looking at your overall sample. Each individual component, what is it contributing? So mass percent says, what is the percentage of mass that each thing is contributing? So N is my subscript for a particular compound. I'm going to multiply that by the molar mass of my element, and then I'm going to divide it by the overall molar mass of my compound. So for a particular compound that is C2H6O, which is ethanol, and this is showing a structural formula and a molecular model, right? Because I have my balls and my sticks here, and this is oxygen, that's hydrogen, and that's carbon, showing how they're connected. So if I have 2 carbon atoms, I take 2 times the mass of carbon found on the periodic table. I divide it by my molar mass, which says 2 times carbon plus 6 times hydrogen plus 1 times oxygen. Adds up to 46.07. So I multiply, I divide, I always multiply by 100 to get to a percent, 52.14%. Hydrogen, I have 6 hydrogen atoms. I multiply it by the molar mass, divide by the molar mass of the compound, times 100% gives me 13.13%. Oxygen, I have 1 oxygen atom, multiplied by its molar mass, divided by the molar mass of the compound, times 100 gives me 34.73%. When we add up our percentages, they need to equal 100% or really, really close. Sometimes with rounding, we might see 99.98% or 99.99, 100.01. These are all acceptable. However, if you were to add up your percentages and you end up with only 89%, or you somehow have 120%, something is wrong and you need to go back and look at your calculation again. Now, we can use mass percent compositions in order to determine an empirical formula. And the steps that you're going to take is to look at your mass percent and you convert that to grams. So if I have a 50% of something and 50% of something else, I just say 50 is 50 grams. The other thing is 50 grams. Or if I had 25% and 75%, I say I have 25 grams of this, I have 75 grams of that. I can convert to moles by dividing by the molar mass of each of those elements. Once I have calculated the moles, I'm going to divide by my smallest number of moles. This is to get to that simplest whole number ratio. Whatever value I get there, that tells me that is the subscript for that particular element. And then I can write out the empirical formula by taking those numbers and putting them as subscripts. Sometimes you don't get an exact number. Like if we divide and you get about 3.01, 3.02, 2.99, 2.98, it's close enough to 3 to make the approximation. However, what happens when we end up with some decimal that's not exactly 3 or 4 or 5? Well, in order to get to the correct formula, then if we look at these fractional subscripts, we multiply by these numbers all the way through to get to a whole number value. So, for practice, butadiene has a mass percent composition of 55.80% carbon, 7.03% hydrogen, and 37.17% oxygen. The molecular weight is 86.09 grams per mole. Determine the empirical formula and molecular formula of butadiene. This is a compound that's found in butter. So, first of all, I look at my percentages and I simply change them into the number. So I just drop the percent sign and say that's how many grams I have, because I'm just going to assume I start with 100 grams because that's just the easiest thing to do. Otherwise, you've got to do some extra math, and who wants to do extra math? So I take these numbers and I make them into grams: 55.80, 7.03, 37.17. This is of carbon. So I look up the molar mass of carbon on the periodic table. I divide to get 4.646 moles of carbon. I do the same thing with hydrogen and oxygen. Divide by the molar mass to get a number of moles. Divide by the molar mass to get a number of moles. Once I've determined the moles of each of my atoms, my elements that I have, I'm going to look for my smallest number and divide it into each of the other numbers. Well, 4.646 versus 6.960 versus 2.323. This is the smallest number. So I simply divide that into each of my other numbers. This is allowing me to find the smallest whole number ratio. We need whole numbers, and it needs to be in its simplest form to have an empirical formula. Dividing out, I get 2 moles, 3 moles, and 1 mole. So my empirical formula is C2H3O. The second part of this problem says the molecular weight is 86.09. So that's going to help me to determine what the molecular formula is, because the molecular formula is either identical to the empirical formula or it's a multiple of those subscripts. So how do I figure that out? Well, I calculate the I calculate the formula mass of my empirical formula. So 2 times carbon plus 3 times hydrogen plus oxygen gives me 43.05 grams per mole. I'm going to take that number and divide it into the molecular mass, because that's going to tell me what is the relationship between these two. And dividing, my grams per mole cancels out, and I end up with approximately 2. So that means that I take and I multiply 2 through my entire subscripts here. So 2 times 2, 2 times 3, and 2 times 1. That gives me my molecular formula of C4H6O2. So this is the true formula of butane-dione, and this is the empirical formula for butane-dione. So keep in mind, anytime you want to find a molecular formula, you look at the empirical formula, you find the mass, and you divide it into the molecular formula mass. Without knowing the molecular formula mass, there's no way to determine the molecular formula. So that has to be given to you.